Okay, we are recording now. Okay, sorry about that. We're reviewing for a test tomorrow, chapter 4 in the Green Book. And we're talking about compositions of functions and inverses and how you get out what you put in. So guys, remember logarithmic and exponential functions with the same bases are also inverses. So if you have 5 raised to log base 5 of z, what would that equal? Z. And if you have log base b of b to the r, what would that be? R. That could have helped you, I think, one of the problems. I think it's number 6 on the review. So we're going to get to the review. The only other thing I said for the kids at home is number 21. If you just change on the review sheet the plus 2 in f of x to plus 18, it works out nice. Okay, so now I'm going to open it up to you guys. What questions you want to go over? Heard 18 first. Going 18. Sorry, too slow. Let me see. 18. 17. Oh, okay, so we want 17, 18, 19, right? Yeah. 17, the answer should be C. Oh, yeah, because I was going to scribble that out. I forgot to. But let me show you how with 17. First of all, when people read it, they didn't know what to make out of it. So just look at the word 17. It says for f of x equal to x e to the x, for what value of x is the slope of the line tangent? What does that mean? Slope, the derivative of the function equal to a half. So we're trying to figure out for what value of x is the derivative equal to a half. Okay? Does everyone see that's what that would mean? So you can either get the derivative yourself, set it equal to a half and solve, or have the calculator graph the derivative. Either way, you're going to have to go to the calculator to answer this question. You're not going to be able to answer this one. You can tell by the choices. So I did want to show you on the calculator what you could do. So if you decided to get the derivative yourself, you'd have to use the product rule, right? And what would the derivative equal? Product rule first, we have the second. So x, e to the x, derivative e to the x is e to the x, right? Plus second derivative of the first, plus e to the x. Okay. So it wouldn't be so bad to get the derivative yourself. The idea is this. We want to know where the derivative equals a half. If you graph them and find out where they intersect, that's where they're equal. So you can put one side in y1, one side in y2, and solve it that way. So I'll show you. Now on mine, what I've done here, instead of getting the derivative myself, x e to the x plus e to the x, it's too lazy. It's using my calculator anyway. So I said to the calculator, hey calculator, you get the derivative, which is this is how you do it. You let y1 be n deriv, remember that's math 8, of x e to the x, but you have to put in comma x, comma x. Then the calculator will graph the derivative of it, right? And then I let y2 equal a half. Now they're equal where they intersect. You guys know how to find out where two graphs intersect? Okay. You don't just trace and guess, oh, it looks like it's around here. You have to use the calc menu. Second, calc, option 5. Is that right? And it'll say first curve, and it'll tell you one of your curves up there. And you press enter. And it'll say second curve. Yeah, that's the second one. Enter. Guess, you just go to where it looks like they intersect. Enter. And that's the x value that makes the derivative equal a half. Negative 0.3149. The other way I could have done it was instead of using that n deriv in y1, I could have just put what the derivative was, x e to the x plus e to the x. So if you'd be more comfortable getting the derivative yourself, instead of using this here, you could just type in x e to the x plus e to the x. Any questions with this? I want to make sure you... So yeah, the answer, I know I have like 2 things circled, just it's the C there. I circled the wrong thing. Okay. So that was 17. 18. 18 was fun too? Good. I like that one. So 18, again, you got to get through the words. It says, what is the slope of the tangent? So what's the derivative of f of x equals the ln of cosine x at pi over 6? So they're asking us for the derivative at pi over 6. Okay? But first you have to get the derivative. So how do you find the derivative of the ln of u? U prime over u. So the u is down here, a negative sign. Yeah, and you could write this as negative tangent. So we got the derivative. It's negative tan x. They asked us for the slope of the tangent, the derivative at pi over 6. So it's negative tan pi over 6. Pi over 6, 180 over 6 is 30 degrees. So I don't know if you remember for 30 degrees, pi over 6, sine, cosine, I gotta extend this. I want to remember that little chart you guys used to have. Yeah. And then tan. You never did the chart? The sine of 30 is a half. Rad 3 over 2. And tan is just this one over that one. Sine over cosine. So it's 1 over rad 3. Because the 2's would cancel. Right? If you have 1/2 over rad 3 over 2, if you multiply top and bottom by 2, it's 1 over rad 3 or rad 3 over 3. Yeah, right, because this is negative here. So we have negative 1 over rad 3, or if you like, negative rad 3 over 3, if you rationalize the denominator. Good one. Yeah, I want to go over 19 first, and then we'll go over, yeah, I definitely want to go over that one. Okay, so 19, they're asking us for this limit. In fact, the limit that they're asking us for, sine squared 3x plus 3h minus sine squared 3x over h. Tried to plug 0 in for all the h's, and guess what I got? 0 over 0. See, if I got 0, I'd be done. 0 over 0. But then I started thinking, boy, this reminds me of like a really good friend I used to know. I don't know if you knew this guy. This guy was great. Remember, it started out, we knew his friend. It was just the old slope formula, slope between 2 points. But then we put the limit as h approaches 0 in front, and that changed our world. Instead of getting a slope between 2 different points, we found the slope at a single point. We found the slope of the tangent, right? Best. So what is this all equal? What was this the definition of? The derivative, right? This whole limit was a definition of the derivative. Now that is because this reminds me of this. I'm like, wait a minute. If this whole limit equals the derivative of that function, what do you think this whole limit equals? The derivative of that function. So we just got to figure out what the derivative of sine squared of 3x is. And we got it. So before we take the derivative of sine squared 3x, we are going to write it as sine of 3x squared. Got to make it a little friendly. All right. Now it's just chain. What's the derivative of sine squared of 3x or sine of 3x squared? What's the first layer? 2. We leave the inside alone, right? Sine of 3x to the first. Okay, what's the next layer? The sine, so the derivative is cosine. So it's times the cosine, leave its inside alone, 3x, times 3. Then you're done. Don't do 3 again. All right, so the constants, you can move up front and make it 6. Yes. Yeah. Yep. You gotta love that. Yes. Yeah, because on this test tomorrow, you don't have to simplify. No, I should say yeah. Okay, what was the next one we want? I know we wanted the inverse one. 21? I'm sure people had problems on 20. Yeah, I know you did. Yeah, you did. You so had problems on that one. Oh. I got one. It wasn't as nice as the one I sent. That's what I'm going to say. Non-appreciative person. Okay, so in 20, h of x equals g. They have this big table, right? But before you, then they're asking you to find h prime of 1. You can't get h prime of any number until you find out the rule for h prime of x, right? So you have to decide what rule. And I know people get confused between product rule and chain rule sometimes, right? You got it? Oh. Right, so how do you know that this is chain rule and not product? What would make it product rule? What would we need so it's a product? Yeah, if it was a g of x, see, if this said g of x times f of x, that's a product. Then we would use the product rule. But this is not g of x times f of x. This is g of f of x. We're plugging f of x into g. So this is definitely chain rule. So chain rule says you take the derivative of the outer function, leave the inside alone, times the derivative of the inside function. So derivative of the outer function would be, there's g prime, right? But you don't take g prime of the derivative of the inside, no. You just of the original inside, right? So you leave that inside alone. So g prime of f of x times the derivative of the inside times f prime of x. Good. Then you can figure out what h prime of 1 is, because it's g prime of f of 1. So we'll have to get f of 1, and then we're going to multiply it by f prime of 1. So now you look at the little chart, and you find f of 1, which is 2, I believe. So we need to get g prime of 2, and f prime of 1 is 3. Now g prime of 2 is negative 3. So we get negative 3 times 3, which equals negative 9. How's that? Very good. I should have waited till tonight. I'm crammed. Okay, we're going to do 21. I know, but is there any question on that? So you got to get the rule first. If it's a quotient, use the quotient rule. Composition, use chain rule. Product, use product rule. Whatever it is, get the rule first, then plug in the numbers and use those numbers. Okay. Ready to do 21? So 21, if anyone came in later, they were zoning out. I had to change the problem so that it wouldn't be undefined. So they say you have this function, and I changed it to x cubed minus 3x squared plus 18. And they say that g is the inverse. So it's another way of calling it f to the negative 1. And we want to find the derivative of the inverse at negative 2. So remember with inverse functions, you know, if you have some function, I don't know what this one looks like, and you have its inverse, which we're calling g, if you have to find the derivative of the inverse somewhere, you can just find the derivative of the function, okay, but we're going to flip it. All right, so if you have to find the derivative of the inverse at some value, at some point a, b, what you do is you find the slope of the inverse of it, and then take the reciprocal. We had like that 4-step approach. So the first step, basically, is if they're asking you to find the derivative of the inverse at negative 2, well, that's the negative 2 over here. That's this x. which means it's the y for the original function. So the first step is you just take the number they give you, the x value, and put it in for y of your original. And then you solve it, and I try to give you ones where you can kind of guess and check. So 0, it's cubic, you're not going to be able to factor it. I think -2 worked for this one. If you try -2, -2 cubed minus 3 times -2 plus 20. Thank you. So this would be -8. This would be 4 times -3. That's -12. All right, yeah, that does work. So x equals -2 is a solution. So that's your first step. It's just weird it came out to be the same number. Then what you got to do, you remember you got to take the derivative of the original function. So we're never actually going to get the inverse. Okay, we're going to use the slope on the original function over here and then take the reciprocal. You're sneaky. So you take the derivative of the original function you have. So that's 3x squared minus 6x. Pop the number you just found into it. It's just a bad coincidence it came out to be -2 also. But whatever number you just found, that's the number you plug into the derivative. So 3 times -2 squared minus 6 times -2. So 12 plus 12 is 24. And now we just got to take the reciprocal of that. Remember, we spent 1 day on this. So the answer is 1 over 24, not the negative reciprocal. A lot of kids get confused with that. Now, that's when you want slopes of perpendicular lines or something. The slopes are not negative reciprocals. They're just reciprocals. Okay, they're both positive. Okay, it's just like because you've switched all the x's and y's to get the inverse, the slopes are just reciprocals. Because they wanted the slope on the inverse at -2. Now, this is not to scale, but pretend the axes weren't there. Okay, so they're saying, what's the slope if this is the inverse when its x is -2? Well, I got to find the slope over here and flip it. But the x over here is not necessarily the same. In this case, it happened to be. But whatever the x is here, it's the y over here. So that's why we set the function equal to that number, solved for the x, and it came out to be the same value, unfortunately. Yes. Yep. Okay, now what do you guys want to ask? Because now I think I've answered the ones you've asked so far. Yes, Ryan. Let me see, what was 24? Oh, yeah. Yeah, that'll be equivalent. Yeah. Now, that one, oh, I don't think I have that one up here. But if I instead said instead of saying find the second derivative in terms of x and y, if I said find the second derivative at a particular point, you just plug in the coordinates to the point, right? Guys, now if you see those big problems on the back, that's all that implicit differentiation. Do you remember that? Yeah? Good, because those are some big pointers. Those are like 10-point questions. So make sure you're not going to mess up on that. Yeah, there were a couple of them, if you had simplified them, they would have been like 6 and 16 could have been simplified first, but the answers would be equivalent either way. I was wondering if you were interested in seeing 6 or 16 or both, because they do work out to be the same. But I just want to write those two up here, just to make sure that you're 6 and 16. 6 was so funny. I saw so many people just going through it the long way, but it's fine. You know, if you could do it that way, that's fine. It was 7 raised to the log base 7 of 3 ln of x squared. See this first one here in 6, 7 raised to the log base 7 of anything, because these are inverse functions, one undoes the other. So you see how you could just simplify this one first? What would that be? 7 to the log base 7 of 3 ln of x squared. Yeah. And then you could just take the derivative after you simplify. It's not wrong to do the a to the u rule, it's just a lot of work. So if you did it this way and you got your derivative, it's 3 is a constant multiplier. And what's the derivative of ln of x squared? 2x over x squared. So you get 6x over x squared, or 6 over x. That's easier. If you look at the other way, if you simplify afterwards, it is going to equal that. And same thing here, only that one in 16, it's not e to the ln yet. Okay, so you can't simplify it yet, because you can't have, it's e to the ln of anything is the anything. But you got to know how to get rid of that 4. If you're going to try to simplify it has to be e to the ln of it. You can't have anything in there. You guys know your log properties? What? Yeah, you just put it up as the exponent over here. So that's the same as saying y equals e to the ln of x cubed to the 4th. Now you can simplify it. So now it's just the same thing as x cubed to the 4th. Right? These are inverse functions. And when you have exponents to exponents, do you add them or multiply them? Yeah, because this means x cubed times x cubed times x cubed. So that's, or you could use the chain rule as is. But yeah, this would be x to the 12th. And then when you take the derivative, easy schmeezy, right? But if you did it the other way, it's fine. If you didn't simplify first. But you should always look out for functions of inverse functions, because you can simplify them. Save yourself some troubles. Sure. Anyone in particular, or you want me to make up a different one, or 24? Okay. You asked for it. So yeah, have this 4x squared minus 9y squared equals 4. All right, so it's not y equals, it's implicitly defined. So you have to remember, with implicit differentiation, when you take the derivative with respect to x, okay, that means you're going to be going d over dx. If you take the derivative with respect to x of x, that's just 1, right? But if you take the derivative with respect to x of y, that's dy dx, right? So the derivative of y is dy dx. The derivative of x with respect to x is 1. And you have to remember that when you take the derivative implicitly. So you go to take the derivative of 4x squared, and you just use your power rule, right? 8x. You don't have to worry about saying times dx dx. That's 1. But you go to the next term, you take the derivative, 18y to the first, dy dx. If you don't remember that, you'll have nothing to solve for. And don't forget to take the derivative of the constant. Don't forget that. See it so many times. And then the whole thing with implicit, if you have to distribute, you do that. You don't here, but you want all your dy dx terms on one side, and the terms on the other side. Right? So it doesn't matter which side. Where do you want me to? Do you want me to subtract the 8x or add the 18y dy dx? All right. Add the 18y dy dx. So we're going to get the y dx terms on the right this time. I'm actually writing it out. I never do that. Okay, so we've got 8x equals positive 18y dy dx. And then we can divide, right? And, you know, you don't have to, but it would be easier. It's always good if you can simplify. So I'm just going to switch sides. I like the dy dx on this side now. So I could write 8x over 18y, but 2 goes into both of them. So we can write 4x over 9y. And that's our first derivative. Now you want to get the second derivative. So you take the derivative of the first derivative. Do you remember how to write the second derivative? Right? Yeah, the squared goes after the d in the numerator and after x. So the derivative of the first derivative is the second derivative, and that's how we write it. And then what are you going to have to do on that side? Quotient rule. So we start low, d high, 4, less, high is 4x. What's d low? 9 dy dx. You don't want to forget that dy dx. Every time you take the derivative of y, you're going to have a dy dx. Go all over the denominator squared. 81y squared. If you don't put parentheses, you have to write 81y squared, or else you have to write the 9y. I think I'm going to do that. Like if you just write a 9y squared, and in your head you're thinking, I know I'm squaring the whole thing. Nope. You either use parentheses or you square it out. Those are the only choices. Okay. Now, if the directions are get the derivative in terms of x and y, all I have to do is substitute in for my dy dx. That's it. I should clean this up a little bit. So let's see, I have 36y minus 30. I don't even know why I'm multiplying. I'm going to cancel in a second. Oh, well, 36x. The dy dx spot is just 4x over 9y over 81y squared. Now, the only thing is, see, that's why I'm saying I shouldn't multiply here. 9 goes into 9 once, into 36 4 times. The other thing is, you know, if not for this test, I'm not going to take, you know, if you don't simplify, but it's just kind of bad form to leave complex fractions. What could you multiply through by so that you wouldn't have this over y over there? Yeah, if you multiply top and bottom every term by y, you know, you distribute the y here, and you multiply the denominator by y, you're multiplying by 1. Something over itself is 1. But then it'll look nicer. So you distribute, you have 36y squared. Now this was 16x squared over y, but when I multiply it by the y, good. And then down here, if I multiply by y, 81y cubed. That's very pretty. And then you could just cancel stuff. You could just start doing stuff like this. You know. Oh, yeah, don't do that. Yes. I'd love to go over 22. 22, yes. So it's implicit again. Getting it? Whenever I have to take the derivative implicitly, I always check to see if y is inside of another function, like it is here. Like you see it's the cosine of xy, y is inside. I know I'm going to have to take that extra step to distribute when it's like that. That's no biggie. So when you want to get the derivative implicitly, you take the derivative of both sides, obeying all your rules. So the derivative of x to the 4th. Good. Now we got a little chain rule going on here. What's the derivative of cosine? Negative sign, so it'll be minus negative sign, so positive sign, don't change the angle, right? Leave the inside alone, times the derivative of the inside. What do we need? Product rule. So we need first derivative of the second. You see the derivative of y is dy dx? Plus the second y times derivative of the first, 1. Okay, so far we've taken the derivative of the x to the fourth. We took the derivative of the cosine of xy, right, with the chain rule. We still have to take the derivative of minus y squared. So that's going to be minus 2y, but we're not done. Dy dx equals 0. Okay. So this is what I'm talking about. When you see that y is inside of another function, after you take the derivative of both sides, you're going to have to distribute before you can get the dy dx terms on one side and the non-dy dx terms on the other. You see how the product rule here, we have a sum? We're going to distribute the sine of xy over this sum, because we multiply. So when we distribute, we have the 4x cubed plus the sine of xy times x dy dx plus, now we're going to distribute to the second term, the sine of xy times y. And then we still have the minus 2y dy dx equals 0. Get your way here. Now we want the dy dx terms on one side and every term that doesn't have a dy dx to go to the other side. The terms that have a dy dx that we're going to keep on the left are this one and this one. The two that we have to move by adding their opposites are this one and this one. Those will subtract, the ones I've underlined in red will move to the other side. And that way, all the terms on the left will have a dy dx, which we can factor out. So I'll still have on the left a sine of xy times x dy dx, and I'll still have the minus 2y dy dx. But on the other side, I'll have a negative 4x cubed minus sine of xy times y. See, the signs change, they're subtracted. Now on the left, because I only have dy dx terms, I can factor it out. So if we factor out the dy dx, which is what we're looking for, what's the other factor going to be? When we factor out the first term, we got sine of xy times x, nice, minus 2, minus 2y. Good. The other side we leave, negative 4x cubed minus the sine of xy times y, and never multiplies, something that's in the angle by something else. I'm trying to make a y squared. And then what's your last step to solve for dy dx? Divide. So we'll just divide both sides by the sine of xy times x minus 2y. That'll cancel it out. So we have the sine of xy times x minus 2y. And that's the derivative. You're welcome. One more. Tell me. Which one? Which one? Okay, yeah. We can do it. So you have this circle. Not that it matters. X squared plus y squared equals 169, radius of 13. But we want to know the equation at the point 5, negative 12. We want the equation of the tangent line and the normal line, right? You have the ingredients for almost the whole thing. If both those lines go through the point 5, negative 12, both of them are going to start out the same way. So it's going to be y plus 12. Remember point slope form? Equals, now the slope we got to get, but what's the rest of it going to be? Yeah, so they're both going to be y plus 12 equals, we'll get the slope, and here we'll have x minus 5. Now to get the slope of the tangent line, we're going to get the derivative and plug in 5 for x and negative 12 for y. And we'll get that slope. Once we know that slope, what do we do to it to get the slope of the normal line? That's negative reciprocal. So to get the derivative, we use implicit. The equation is x squared plus y squared equals 169. So the derivative, we differentiate, we get 2x plus 2y dy dx equals 0. Okay, we move the 2x to the other side, so it'll be negative. So we have 2y dy dx equals negative 2x. We didn't even have to pull it out. There's just one term. We just divide each side by 2y. And so our derivative equals negative x over y. But we want to know the slope at the point 5, negative 12. We want the derivative evaluated at the point 5, negative 12. So we have negative x, so negative 5 over negative 12, which is just 5 twelfths. So the slope of our tangent line is 5 twelfths. So the slope of our tangent line is 5 twelfths. What's the slope of the normal line? Negative 12 fifths. Whew, I just made it. So study, you'll be fine. Right? See you later. Oh yeah, I have extra help today. Where is it?